required for a deadlock? Name one. Non-preemptiveness, yes. Hold and wait. Circular weight. Okay. Anything else? There are 4 conditions required for a deadlock. We got the circular weight, the non-preemptiveness. Hold and wait. Yeah, I said that. That doesn't count. Mutual exclusion. Right. Explain to me. What do we mean by mutual exclusive device?
That the device can only be used by one process at a time.
At a time, yeah, perfect. A device which can only be used by one user at any given time. Right. Preemptive system. What's a preemptive system?
System where a process can be interrupted and the resources taken from it.
Right. Okay. A circular weight. What's a circular weight?
It's when one or more processes are waiting
Another process that's waiting for another resource. And where does it end? Does it go indefinitely? One is waiting on the next, one is waiting on the next. And they go back to another point. They go back to the first point. So that's these are the 3 conditions. Right. What's a virtual device? I'll be back to you. A virtual device? No, I have to go back this way. Yeah, sorry. I have another question for you.
Dedicated device that appears to be like a shared device.
It's a device that by its nature is a dedicated device, but we use it as if it's a shareable device. That's a virtual device. Right. And what's spooling? Anybody?
Printers, and it's the same idea as a virtual device. The printer is a dedicated device, and it gives the appearance that it is shared.
Okay. Yeah, so it's a technique used for printers to allow or make printers that are normally, by their nature, they're dedicated devices that can be shared or appear to be shareable simultaneously. Right, okay. How can we how can we prevent a deadlock from ever happening in a system? Spooling is a mechanism that's used to turn a printer from a dedicated device into a shareable device. Hold on. Yeah? To solve?
One of the conditions is...
Yeah. Go on, yeah. How do we prevent a deadlock in a system?
If one of the conditions, of the 4 conditions doesn't come to be,
Yeah.
we can prevent it.
If we can, what do you mean prevent it? Now here, this gentleman here, what do we mean by preventing a system? He said one of the conditions prevent it.
If you remove one of the conditions that causes a deadlock, then the deadlock will.
Okay, so those 4 conditions that are the 4 of them are necessary to be present in a system in order for a deadlock to happen. If we can make sure one of those conditions does not exist in a system, then we will never have a deadlock. Okay, so for example, one example is that we might decide to remove a circular weight from a system. Anybody knows how could we remove a circular weight? Make sure that our processes and resource requirements never go back to the same point. Any ideas? No, hold on, I have a volunteer here. Yeah.
Locking the resource, if it gets a request from one, it's locked from a request from...
Oh, locking...
Or putting them in order either as well, so you can't access the other resources without...
Exactly, yeah. So arrange your resources in a system, all the resources in some order, that any user, any process that needs more than one of those resources has to take them in that particular order. Maybe the highest order first or lowest. Okay. How do we avoid deadlocks? Have we talked about deadlock avoidance? Using Banker's algorithm. Thank you. Who can tell me Banker's algorithm? Any volunteers?
If you have a request, you make sure that you can satisfy it, and if you can't, you make the request wait.
Not quite.
It's like that's the.
If there is a request,
safe state.
yeah.
Like if there is a safe state, then it will prevent the deadlock.
Satisfying the request will leave the system in a safe state, then the request will be satisfied. And it's not
Exactly. If we receive a request, we see if we satisfy that request, will it turn the system into a safe state or unsafe state? If it leaves the system in a safe state, well then we will satisfy that request. Okay. Otherwise, we'll refuse the request. Okay. Very good. Very good. What else have we talked about? Did we talk about starvation as opposed to deadlock? No, we just talked about deadlocks, right? Anybody tell me what a deadlock is? What is a deadlock?
Deadlock is when all the four
Well, that's when it will happen. When the four conditions are present in a system, then we're going to have a deadlock. But what is a deadlock? Yeah?
When John Moore process is trying to access the same allocation for each of them.
Okay, so that's a circular kind of weight. Yeah? Okay. Anybody can tell me what a deadlock is? Maybe it's a number of things, but it's first, a deadlock doesn't happen to a single process. It happens to two or more processes. And it's a system-wide kind of tangle resources. So it's kind of, some call it the deadly embrace, where resources and processes kind of get into some sort of position that they cannot get out of. And they're all waiting. All the processes in a deadlock, they're not executing. They're asleep, waiting for something that is never going to be available. And how long does it take before they actually get out of that deadlock? Normally, under their own power. They'll never come out of that deadlock. So it's there forever, unless acted upon by an external force, unless somebody from outside those deadlocked processes comes up and solves them. So what we talk about today, hopefully, is how to how to detect deadlocks and how to actually solve or come out of a deadlock, and how to handle them. So I'll just talk about it briefly and then we'll put the slides on. So I need the light here just for a minute. Is that okay? Or does it affect the reflection? Or see if the students can see it. Okay, so and while I'm just organizing my markers here, just can you tell me what a quantum is? A maximum time that a process is allowed to have a processor. And what's a CPU bound process?
Our processes are use more the CPU than the other
Than IO. So processes that use more CPU or longer CPU cycle and shorter IO cycle would be CPU bound processes. Okay, so what are we going to talk about? How do you actually to detect a deadlock? So to detect a deadlock, there's an algorithm used which can be programmed to actually detect the deadlock, but one of the ways it's done is an implementation of the directed graph. So we can use the directed graph to represent the actual processes and the resources. So we're going to need 4 kind of symbols that we use for those graphs. A circle usually represents a process, a square which normally would represent a resource, and an arrow which normally if it goes from a resource to a process, it means it's allocated. So in this case here, resource 1 is allocated to process 1. And if the arrow is going from the process to the resource, we can say that this process is actually requesting resource 1. It needs resource 1, puts in a request for it. So these are 3 symbols. The last symbol is a cluster resource, or cluster of resources where we might have 2 or 3 similar resources. Let's say we have 3 printers that are exactly the same, identical, and each one of those will be an instance of this resource. So, and it doesn't make much difference to any user which of those 3 printers, for example, to use, or which of those 3 resources to use. But now this cluster can actually accommodate maybe 3 different requests, maybe from 3 different processes. So you need to be able to draw a diagram or the graph from a number of, say, instructions or statements. So if I say, for example, process number 1 is allocated, or resource 1 is allocated to process 1. So you write, that's the resource 1, and it's allocated to process 1. And there we are. So that is an implementation of that statement. And if we say process number 1 is requesting resource 2, so you draw resource 2, like a square kind of, and you have to have an arrow going from the process to the resource. And that is process number 1 is requesting resource 2. So the arrows are the same, but it depends where is it going. If it's going from a process to a resource, then this process needs that resource, and it's requesting that resource. If the arrow going from the resource to the process, then that resource is allocated to this process. It has it. So this image now, it seems to show us that there's a process that needs 2 resources. It already has one of them. It has resource 1, but it doesn't have resource number 2. If it's free, we'll reverse the arrow and make it allocated to the process. Otherwise, but maybe the next statement is resource number 2 is actually allocated to process number 2. So process 1 cannot have it. It's already been allocated to process 2, and we don't have a preemptive system. This is a non-preemptive system. We cannot take that resource. So in this case here, process number 1 has to go in a waiting state until this resource becomes available. And this is just a sample of the directed graph. So let's say we have 2 resources in a cluster of resources. They are similar resources. Process number 2 has one of those. One of those resources allocated to process 1, but another process, process number 3, is requesting, say, this resource, needs this resource, and possibly has this resource. So that's another incident. Yeah?
What's the meaning of that symbol, the square with the...
This one here? This is a cluster of resources. Cluster. As group of resources that are there exactly the same. So maybe there are 2 printers we have, so we can say, right, they can be, now these 2 printers actually in the allocation, it goes, you even point out which printer is being, which instant of that resource is allocated to which. But it doesn't make much difference. Any one of them would do the job. So in this case here, this printer, for example, or this instant of this resource is allocated to process 2, that one is allocated to process 3. Right, and then if we can keep on drawing the diagrams of the system based on all the processes that we have and all the resources, and we show which one is allocated to which, and which one is waiting on which, and which one is requesting which, right? So requests and allocations. And once we finish the diagram, then we check to see if there is a deadlock in the system. And the way to do it is to try to eliminate, to remove, wipe off the diagram, the links. If we can remove all the links, then we'll say there is no deadlock in the system. If we cannot get rid of all the links, that means there is a deadlock in the system. How do we remove the links? Is by checking. We start with the processes. The step is to start with the process that has all the resources it needs. So in this example, we can start with process 1. We look at it. Does it have everything it needs? Process 1 needs 2 resources. It has one of them. That's resource 1 is already allocated to it. It has that. But it does not have resource 2. It's requesting resource 2. Can we allocate it to it? No, we cannot. It's already allocated to another process. So we leave process 1. So we go to the next process. If you can spot a process immediately that only needs 1 resource and has it, or 2 resources and has them, then we immediately start with it. So in this case here, if I go to process 3 has this resource, but it needs another resource which cannot be allocated to it because it's already allocated to another process, so we leave that. So we go to the next process, process 2. As we can see, process 2 needs 2 resources, and it has the 2 resources. So this could be a file, this could be a printer, so it's actually going to be reading from one file and sending to the printer, maybe, or copying one file right into a hard disk. Whatever these 2 resources are, it doesn't matter. It has the 2 resources it needs. So sooner or later, it's going to finish. It's not going to wait on anything. It's not going to be interrupted, and we're not going to be emptying it from, we're not going to be taking any of the resources out. So once we say sooner or later it's going to finish, when it finishes, we'll step ahead in time and say when it finishes, it will relinquish these resources. It will release these resources voluntarily. And therefore, we can remove those links. It no longer has those resources allocated to it. We can even wipe the process itself if we like. I'll leave it just so we'd know we had a process here that was working. Now, those 2 links, the resources that were released, we can see, is there any other process that needs them, and we allocate them to the next process. So this one, there's nobody requesting this, only process 3, and it has 1. We have a now spare printer or spare device there. But looking at this resource here, this is resource 3, by the way. Looking at resource number 2, it's free now, and it's requested by process 1. So what we can do is say, we can allocate it to process 1. It's available. And then we look at process 1. Process 1 now, it needs only 2 resources, and now it has the 2 resources. So looking ahead in the future, it will, sooner or later, it will finish. So, and when it finishes, it will release those resources. So now resource 1 becomes available. We can allocate it to process 3, and process 3 now will have all the resources it needs, and it will finish, and we can wipe out those links. And if you can look now, there are no more links in the diagram, and therefore we say there is no deadlock. So our system, as it stands at the moment, with all the links, requests, and allocations, is going perfectly. It does not have a deadlock. So we are pretty happy with it. There are some other times or cases or examples where if you try to get rid of these links, you can't get rid of them. And if you cannot get rid of them, then there'll be a deadlock. And you need to know where the deadlock is. The deadlock may not involve all the processes. So I'm going to have another example now. And let's see if it's... So I'm going to go back, allocate this to that one. And I'm going to say allocate this one to this one. This one, let's say, it needs this resource. And it also, this process, what am I doing? 2 resources cannot. So this process needs this resource hated, but this resource is with this process, and this one requires this resource as well. So, okay, let's go this way. Now I look at this system. This is a different system. The question again, you might either be told in statements to draw this diagram, where we'll be told, for example, process 1 is request and resource 1. Resource 1 is allocated to process 2. Process 2 needs an instance of resource 3, and so on. And you draw this diagram, or you might even be allocated given the diagram, and you're told, is there a deadlock in this system? Yeah?
Sorry, when we are able to remove all the links, so...
There is no deadlock.
There is no deadlock.
Exactly. Right, so let's try. And that's what we always aim to doing, is try and remove all the links. So let's start. And you can even remove the processes if you like, once it has no more links attached to it. So let's start anywhere with any process that has all the links it needs. So this process here needs 3 links, or it has needs 3 resources. It asks for this one, but this one is not available. It requests this one, but that one is not available. It's already allocated to another process. It needs this one, and it already has it, but it cannot finish. So we cannot clear the links of process 3. Those 2 resources are not available yet. So we go to another process. This process here only needs 2 resources. It needs this one, and it has it, but it doesn't have this one because it's already allocated to that process. So we cannot wipe this out. This process here, it needs 3 resources. It has this one, and it has this one, but it needs that one, it doesn't have it. That one is allocated to this one. So if we just follow this kind of a process, we see how it goes. This one needs this resource, which is allocated to this one. And this one, in order to finish, it needs this resource, but it can't have it. It's already allocated to this one. We're back at the same point where we started. If we can go around like this, that's what we call a circular wait. It doesn't necessarily have to be a circle, but as long as you can follow these allocations and requests, and if they bring you to the same point, then that's a circular wait, and that's a deadlock. And we can't get rid of any of the links here, and therefore there is a deadlock. And the deadlock, you follow it, it's identified as follows. It's P1, R1, P2, R2. And then it goes back to P1, R1. Okay? So this is the detection of a deadlock, to know whether there is a deadlock in the system or not. And if there is, what are the processes that are deadlocked?
Just to get it right. So when there is a circular wait, it means there is a deadlock.
Absolutely. Yeah, in the graph here. And when you cannot get rid of these links, if there is, but you can get rid of them first, well, then get rid of them. But if you cannot get rid of them and you're left with this circular wait, then that is a deadlock. And you need to identify these processes by following the circular link, the circular wait, that you'll find that these are the processes that are deadlocked. This process, those process, and that resource, and that resource. Okay? Now, the next point that we need to check, once we are able to detect, we'll have a look at a few more examples later, but once we are able to detect that there is a deadlock, once we know that there is a deadlock, because sometimes it's very difficult to know, because you might have 60 processes running, and there's only about 4 of them that are deadlocked. The other 56 of them are running, executing, printing, and saving data on the hard disks. Everything is really working except those 4, and it's very, very difficult to figure out. So you could run those algorithms or those processes every now and again to see the deadlock detectors. And that's basically what they do in a software kind of fashion. But once you identified the processes that are deadlocked, then we need to be able to handle. But how do we actually recover from a deadlock? If these processes are deadlocked, how are we going to get out of the deadlock? And the simple answer, there's no easy way, there's no cheap way of getting out of a deadlock. A deadlock just involves a number of processes that are waiting. And sleep, basically they're like asleep. Each one is waiting on the other, and they're never going to come out of that on their own, under their own kind of power. So we have to do something in order to come out of that. Some people say, right, insert a few more or add a few more resources, but you may not, and most of the time you don't have more resources. You don't have another resource number similar to number 2 that you can just decide, okay, here's resource number 5. But sometimes maybe you have 50 other processes running, and maybe one of them is using another resource that at the moment similar to this one. So this one, instead of waiting on that one, another very similar resource will become available. Because remember, we have lots of other processes executing at the same time, and the others are running. They're not deadlocked. So maybe if what some systems say, right, just stop any more new processes coming in. Let's just get those that are running, let them terminate, and maybe, just maybe, one of those resources is going to become available that we will be able to say, right, you're waiting on this one, but instead we'll give you that one. It's exactly the same. So that's one way of doing it. But then that's even a more complex way of doing it. But normally, it involves just switching all the processes off. A lot of the times actually turning your computer off, reaching for the power button, hit the power button, everything's down, reboot the computer, everything starts again. So all these 50 or 60 processes, they all stop working and they all start again. Of course, that's not a very good or efficient way of doing it. Yeah?
Can it cause system break or an error in the system, this kind of?
The problem with deadlocks, they never give you error. They don't give you an error. They're just processes waiting for which is a normal thing to do, to sit and wait for some resource.
Down the performance of the computer maybe, but
maybe if they're holding somewhere, but normally the other processes are not really affected. In fact, probably they won't slow down there because they don't even use the CPU, so they're asleep. They never come out of their kind of wait condition. Each one of those 2, for example, here, each one of those 2 is waiting on one of those resources. And these resources are held by the other one, and they never come out of that. And they're not using CPU, they're using nothing, they just sleep. So they don't give you an error. So because it is not an error, normally, under normal circumstances, it's normal for a process waiting for a resource to wait for a little while and then get it. But it's just this little while becomes a very long while and becomes forever. So there's no error as such, unless if we can, develop a system and say, hey, if you go waiting for longer than certain time, maybe we'll give an error. But the basic now idea to get out of a deadlock is actually to maybe terminate all processes. But some of the processes have been doing a good bit of work, and then turn it off to start again. It's going to, waste all that work. It's going to have to be repeated. So what they say, again, it's better not to turn the entire system off. Just look for the ones that are deadlocked. If you can identify them, maybe 4 or 5 or 6 processes, just terminate those instead of terminating all the entire processes that are executed, especially the ones that are running, let them run. So, but again, even those 5 or 6 processes that are deadlocked, if they get terminated, some of them could have done a lot of work, and some of them by actually terminating them, you're actually causing a problem because they'll need to run again, and by running again, they might cause data error. Like if you are adding a value, if it's adding value to each record, and then before it finishes adding it to all the records, if it breaks down, then runs again, it will add the value to the same records again. So you might get wrong results. That may not be the right thing to do. So, the better way is even to analyze those processes and pick only one, terminate one process at a time. Decide which process to terminate, and hopefully that will clear the deadlock. And if it doesn't, then pick the next victim to terminate. So really, in getting out, recovering from a deadlock, the only thing to do is actually picking the right victim to get out of this deadlock. And the right victim is which process you'd select that will terminate the system, but at the minimum cost, the minimum damage cost to your system. It's just a matter of damage minimization rather than, solution. It's not a good solution, but it's better than nothing. Yeah?
Actually, can we terminate a process manually?
You can, the system administrator, there'll be a process. I don't know, in Windows you can actually hit Control Alt and Delete and you get the processes and select one process and terminate it instead of terminating the entire system. But yeah, in every operating system there'll be a way of picking which process you want to terminate. They could all be running or waiting, but they're all there in the system, you could see them. But if you knew which ones that are deadlocked, you can identify the one. Usually there is an ID that will give you the process ID, and you can terminate it. So the point here is just a matter of selecting which process is the best process to pick or to select as the victim to terminate, and that will give us the least amount of damage. So, obviously, for example, if a process has been running for 10 minutes, real long time, it's done a lot of work, and another process that are deadlocked, another process just started like 1,000 of a second ago, didn't do much work at all. So by actually which one would you rather to terminate and start running again? So obviously the one that's done a lot of work, try to leave it and terminate the ones that hasn't done much work. So whenever you run them again, and we assume they need to be run again, then you wouldn't have lost a lot of the work that was done, a lot of the CPU time or a lot of the processing that was done. Anybody can come think of any ideas? If you want to evaluate or if you want to select between a number of processes, how would you select? What criteria would you use and which one would you select?
Priority.
Maybe priority. Obviously, yeah, if you have different priorities in the system, if the system uses priorities, so the very important processes that with the high priority, don't touch them, go for the lowest priority one. Usually they are ones that they have very little value, they don't do a lot in the system, and normally they'd be very small and minimum damage. Yeah, okay. Any other suggestions? It's what? Yeah, very good. You pick the processes that has more, say, resources than waiting. Let's say this process, for example, maybe, I don't know if this is what you meant, but this process has 6 resources and this process has 2 resources, for example. And they're equal, they have the same priority, but this one has 6 resources. So if you probably release this process, it probably has more chance of those resources that it releases that which will allow many other processes that are deadlocked to be released. It has a better chance of terminating the deadlock rather than that one. So maybe, yeah, that's a good idea. Or if you knew for certain, if you release this process, it's going to release that resource that's going to be used by this process for certain, well then we'll go and terminate it. So if you know for certain, that's a better process to terminate because of the resources it's holding. They will solve our deadlock, yeah. If not, go for the one that's holding the larger number of resources rather than the one that only has 1 or 2 resources. Yeah, good. Any other suggestions? So priorities, number of resources. Any other? The length of time that they've been running on the CPU used. Try to go for the one that hasn't used much time or hasn't wasted a lot of resources. So even if we have to start it, we wouldn't be repeating a lot of the work.
Well, and the waiting time, that
No, CPU time.
Specify a time that each.
If we knew this, see, usually in most operating systems they'd have statistics and log of each process, how much CPU time it has used up to this point. So if a process has used a lot of CPU time, 3 seconds or 5 seconds, that's a very long time, as opposed to 30 thousandths of a second. So that's a very kind of short time. So the one that has used that one that has done a lot of work, instead of having to repeat all that work, we get the one that has done very little. Because later on, as soon as we've maybe terminated, their owner is going to run it again because they didn't see maybe somebody is executing a process that will display a report for them on the screen and got deadlocked. So if we release it, it's going to go and then run again and produce that report on the screen, rather than one that's been calculating the weather forecast for next week that takes a long time to process and hasn't finished. So now, if you run it again, it's going to run again, use a lot of resources again. So we'll go for select the one that has used less CPU, and hopefully it will cause us less damage or cost. Anything else?
Can we call that process? Can we call any one of the process manually?
Can you halt them manually? Yeah. Well, halt. They're already waiting. They're already asleep. They're not running at that moment. They can never run until that resource becomes available. Do you mean it's already paused? If you mean by pause it, release the resource, well, then we're getting into the non-preemptive and preemptive systems. Remember, this is a non-preemptive system. With some resources, it wouldn't work. Like if it has a printer and it's printed half page and half a line, and then you take the printer and you say, no, let's give it to the other process that start printing on the same page. It's not going to be a very good. Yeah, if it works on the system, yeah. But now there are some processes that are writing, that do actually write information, update databases. Try not to eliminate these or terminate these, because they're going to start rewriting again. And so if you have a process, two processes, one actually writes data and updates records or sales into a database, and another one that just opens a file, reads it, and display on the screen. If you run this again, nothing's going to change. You're even going to get a better, more up-to-date report. While with the other one, if it had updated 100 records, and now you're going to run it again later, it might update those 100 records again, and you might end up with the wrong results altogether. So, as a general rule, don't terminate processes that actually write data to files. Maybe ones that read from files, that's okay, you can terminate them. What other? So these are guidelines. So you can see later on in the notes maybe more guidelines as to what processes that you'd select as victims to terminate the deadlock. But remember, deadlock, there's no way, no cheap way actually of getting out of a deadlock, recovering from a deadlock, except by terminating processes. Right. Finally, we talk about starvation for a little bit, and starvation as opposed to deadlocks. And starvation, the major difference. Starvation is actually starving or withholding a resource from a process. So a process is denied the access of some resource or more for a long period of time, sometimes forever. So that's called starvation. So what's the difference between starvation and deadlock? Deadlock is almost similar. There's a process that eventually, or more, in deadlock, the only thing in it says there at least 2 processes or more. You can't say a process needs a resource, it's deadlocked. But in starvation, you can say, yeah, there may be a single process that needs a resource. That resource is not available, and it gets starved from that resource. But in a deadlock, you can never say one. There has to be at least 2 or more processes that get into a situation where one has a resource that and meets another one that's held by another process. So they go into this chain effect back into a reverse, back to where they started, into what's known as a circular wait. And that's what a deadlock is. So a deadlock involves more than one process, 2 or more. And they get kind of all plugged up in a waiting situation based on circular wait of resource. But starvation can happen to one or more processes, obviously. And starvation can also is something that's not recommended in a system. Maybe a process may be starved because of its priority, so it doesn't get resources because other processes are more important, and there's always more important processes that keep going ahead, and it gets starved. And there's an example that there's an example of these people who are supposed to be thinkers and that are sitting around a meal, 5 monks who actually meditate or think a lot, and then every now and again they feel hungry, so they decide to eat. And it's an old Chinese story well around it. And there's a big bowl of rice, and they have the chopsticks, and their chopsticks are available. So anytime the guy feels hungry, sits and meditates most of the time, and whenever they feel hungry, they reach for the 2 chopsticks, one on either side, eat the rice, and put them back down here. So maybe the neighbor now can, whenever they feel hungry, they can pick the 2 tools here, the 2 chopsticks, and eat. And that's been going on for hundreds of years. Meditating, learning, and eating. That's all they do, think and eat. But recently, they've started having these problems of starvation. They started going real hungry to a point that they nearly die. Or sometimes they even get deadlocked. They never get out of that situation. So these chopsticks resemble the resources that are available. And these are the processes, the users, the monks, the guys who are sitting there and eating. And each time they want to eat, they need the 2 resources. So they reach for this resource, and they use it to eat. But these are, even though they are shareable resources, they share them, but they are mutually exclusive. That means you can only one user at any given time. So this chopstick can either be used by this user, user A, user B, and so on, or this guy here can use them. So whenever this guy starts eating, this one feels hungry, cannot eat because the chopstick is being used by this one. So he says, right, I'll wait for a while, I'll go and meditate. So he goes meditating, and then half an hour later he says, now I'm hungry, I'm going to eat. So he goes out here, picks this chopstick, looks at that one, but finds that his neighbor here is eating, who's got this chopstick. So he says, I'll come back later. And he comes back later, and the other guy is eating. And that's why they ended up starving. So the question now is, we want you to come up with an algorithm or a plan or an idea or rules that they should follow, that hopefully they should never get to a starving situation or a deadlock situation. Now, I'll get to a situation of a deadlock. The example I explained kind of leads to starvation that may never come out of it. This guy may never end up eating because each time he or she wants to eat, the other guy is using it. One of its neighbors is busy eating. So the other possibility is that if all the 5 monks here, they decide, at one moment they say, they're all hungry. They all felt hungry at the same time. And they all felt, right, we're going to start eating now. So each one of them reaches for the first chopstick on their right-hand side, for example, pick it up, and then decides, I'll go for the other one, for the left one. But the left one is already gone by their neighbor who picked it up. So each one of them has one resource, holding onto it, and is seeking the other resource, but it's not available, so he says, I'll wait for my neighbor to finish. But their neighbor is not going to finish because they're also waiting on their neighbor to finish, and then they're going in a circular wait, so all the 4 conditions have become available in this situation. Each one of them is holding one chopstick and not releasing it, and going in a weight situation while holding the first chopstick. But these chopsticks are not shareable. Yeah, they're mutually exclusive. And we end up with the circular weight. So that's an example of a deadlock situation with this example. So we'll go through it and we'll see if there are any solutions to their dilemma. Okay, any questions so far? Well, that's what we need to do for today, for the rest of the day. We've already hopefully covered most of the material we need to cover. Yeah. Okay. What time do we finish today? 5:30? Thank you. Now, what's the difference between deadlock and starvation?
The deadlock involves 2 or more processes, and the starvation is...
It can happen to, yeah. Okay, so we go through the slides. This problem is known as the dining philosopher's problem. So we'll... yeah. Why is it showing the full screen or the 2 screen? Yeah, that's better. Right, okay, let's go through this. We've already gone through it, so this is a good reminder of what we covered. So hopefully, what we've done yesterday and today should give you a good idea about several causes of system deadlocks. Now you should know what could cause a deadlock. And the difference between preventing and avoiding deadlocks, which you should already know. Anybody would remind me how to prevent a deadlock, very briefly? You know how to prevent a deadlock? Make sure we don't have a deadlock in our system? Okay, can you? Any one of the conditions. So just make sure at least one of those 4 necessary conditions is not available. At least one of them is not in the system, then we will never have a deadlock. That's deadlock prevention. Deadlock avoidance. How could we avoid deadlocks? Do you remember? Yeah, I knew you knew it, right? You answered the first thing. The differences between preventing and avoiding deadlocks. We know how to prevent a deadlock, how to and then how to detect and recover from a deadlock. So we've already went through detection of deadlocks by following the diagram and removing all the links and the processes that have finished or no longer needed. And if we can remove all the links, then there's no deadlock. Otherwise, we'll be able to detect the deadlock. And the concept of process starvation and deadlocks. So we also talked about the race problem, racing to change some data. Like we took the example of a bank record being changed simultaneously by two different processes, that you could end up with the wrong balance. That's because the processes are racing to change the data. It depends who gets there first or last. They could get different values. They cannot be, it can be random, whatever final results you get. And obviously that's not a good idea to say, right, once we finish these two processes work, we don't know what's the outcome going to be. We need to be very determined of what the final result is. And then differences between deadlocks and starvation. So right here, a few definitions that explain deadlocks. We'll talk about deadlocks. A deadlock is a system-wide tangle of resource requests that begin when two or more jobs are put on hold or wait. Once you start, need the resources not available, you go on and wait, then you're starting the first step towards a deadlock. And then each job waiting for a vital resource to become available, but the job comes to a standstill. All jobs, eventually they halt, they stop working, and they never come out of it if they go in a circular way. It can only be resolved or removed. The deadlock can only be removed by external intervention. While starvation, when a deadlock happens between two or more jobs, starvation, one particular job may be starved or delayed for infinite length of time. It can be infinitely, forever. So the effects of deadlocks, one or more jobs, hence more serious than starvation. So which one is more dangerous? Obviously, deadlock is more dangerous because it affects normally more than one job. It could be 2, 3, 4, 5, it could be even more. A complete system, not just few jobs, is affected as resources are being tied up. And the problem with this is not just the processes that are waiting, doing nothing, no work. It's the resources as well that are being held by these processes, are not being available to the system. So it becomes even clearer in interactive system because you're waiting for the process. If you just submit a process and you don't expect any results from it for now, maybe after an hour or tomorrow you need the report, then you may not notice it. But if it's an interactive job and you submit it and then you're waiting for something to come back to you, or nothing comes back for a few seconds and reaches a minute, then you say, oh, hold on, there is something wrong. So it's clearer in deadlocks. And there is no simple and immediate solution to a deadlock. It will always involve having to first identify where the processes that are involved in the deadlock, and which we start terminating them one at a time. Hopefully you terminate the first one and the deadlock is sorted out. So this is just another example that explains deadlock. I think possibly, talking about the two chefs, who want to cook the meals, probably is a better example because than this one here. But even though it appears to be here a circular weight, but these here are no longer affected. These other cars are not really part of the deadlock. Just this car needs to get into that position that's now occupied by that car, that needs to get into that position that's occupied by that car up to this point here. But this one is really not part of the deadlock. But anyway, so that's how a deadlock is. Always remember it involves more than one process, more than one resource, and it always involves circular weight. Always involves, it happens in non-preemptive systems. So, and in computer systems, you can have deadlocks in files, in databases, in dedicated devices, obviously printers, multiple devices, spooling, disk sharing, networks, communication lines, anything, any resource that cannot be used simultaneously by more than one user. And once you have to wait, then you're starting to get a step closer into a deadlock. So this gives examples of, say, using files, but they're pretty much the same whether you're using files or printers or in a communication line. As far as we are concerned, they're just resource. So this file 1 or file 2 is just like resource 1, resource 2. If a process needs this resource, in the old days they used to have dotted line for requests, but I mean, nowadays most textbooks, it doesn't matter. It's just one continuous line. Whether it's the direction is what's important. If it's going from a process to a resource, then this process is requesting this resource. If it's from a resource to a process, then this resource is allocated to this process. So you don't have to worry about the dotted line or the continuous line. But that's what a deadlock eventually always ends up into a circular wait. And there can be two processes, but some students, they say, a deadlock is when two processes are interlocked. No, two or more. You can have more than two processes. But we don't need to go through each, if it was files or if it was disks or the locking technique that we talked about. This will solve the problem of accessing the same file. Remember when there's a race problem, when you try to update the same record. So instead of reading the record from here, the balance, and read the balance, write the final balance, locking is the mechanism is used that we talked about. You lock that file. When you finish updating it, then release it. Then only then the other process can look at it, can get the final and correct values from that particular record or file. And we talked about this example of updating a bank account where you might end up getting the wrong results if two processes are lodging, same amounts of money. We said if your balance is €1,000 and you have two processes, each one of them is adding €1,000, you should end up with 3,000. But sometimes you end up with 2,000 because of the lack of synchronization between them, because there was no locking. So in dedicated devices, they can either any kind of device that cannot be shared. If these devices are shareable devices, then there'll never be a deadlock. Always remember this. If the devices are used by more than one process, then we'll never have a deadlock. The deadlock happens because this device can only be used by one user. So when the second user comes in, they have to go in and wait. Once they go in and wait, and you keep getting circular waits, then that's when we have the deadlock. So this is an example where you have more than two processes, actually three processes in this case. They're seeking three different resources, and they go into a deadlock situation. Then here we talked about virtual devices, which is through spooling we can turn the printer. Spooling is an example that's used specifically for printers, to turn a printer, which is normally a dedicated device, to turn it into a usable device or shareable device, or what we know here is a virtual device. So there are a number of examples for deadlocks on networks or on disks or hard disks or files. It's always the same idea. There's a specific resource that cannot be shared, and there are many users that they end up waiting on it. So these are the four required conditions for a deadlock. If we have these four conditions in our system, then we're going to have a deadlock for certain. And these are the conditions. Mutual exclusion, and you need to know what each of those, how to explain each one of those conditions. So mutual exclusive device is a device that can only be used by one user at any given time. It cannot be shared. It cannot be used by multiple users at the same time. Resource holding, or in some textbooks they call it hold and wait. So if you are holding a resource, and you need another resource, but it's not available, you go into a waiting situation or state while holding the first resource. If you're allowed to hold the resource while you're going to wait for another resource, then that's the second condition called resource holding or hold and wait. No preemption. That means that in this system we do not reach to a process, take a resource away from it. And finally, the circular wait, where you can actually follow in a graph a process that has a resource, that needs a resource that's allocated to another process, that needs a resource that's allocated to another process, and then if you can go back to the same point, then you went in a circle, came back, that's known as the circular wait. So if you want to prevent, if you want to make sure our system does not have and never will have a deadlock, just make sure one of these conditions is not present, is not prevailing in our system. So make sure our system does not have devices that are mutually exclusive. That means all the devices we have are shareable devices or virtual devices. Or make sure that if a process has a resource and needs another resource, needs to go wait for it, it has to release this resource, can't go waiting, holding another resource. If we can do that, then we'll never have a deadlock. And similarly with no preemption, if we allow, if a process is sitting waiting with 3 resources, it's told them if we can take away any of these resources from that process, this is very difficult and very dodgy, very difficult to implement. Because if a process started printing and then halfway through you take that printer from it, it's very difficult. But there are ways to get around it. And the circular wait, obviously, if we can prevent that. And we know how to prevent each one of those 4 conditions. Everybody's happy? And remember how to remove each one of those conditions from a system? Is there anything that you do not remember? How to remove mutual exclusion or resource holding or non-preemption or circular wait? Okay, so you're all happy. So if I ask you, how do we actually eliminate this from the system, you should be able to remember. And it's explained there, so you can go through it there, of the methods of how to do it. Then this is the directed graphs. So just an example of how to actually display or draw the graph based on certain statements. So if you get this statement, process 1 requests and is allocated resource 1, well then that's actually drawn by this way here. So this process 1 is allocated resource 1. It's requested this resource, but now this resource is allocated to this process. And similarly with resource 2 is allocated resource. You keep drawing the diagram until all the statements are fulfilled. And this is a cluster of resources where we have the same instances of multiple instances of the same resource. The number of dots or circles inside the box will show the number of instances of that resource. So we talked about prevention of deadlock, and we prevent a deadlock by making certain one of those 4 important conditions is not in the system, at least one of them. Avoiding deadlock, that's by implementing the banker's algorithm. The detection is by implementing the graphs, the directed graphs. So the prevention, just excluding or removing one of those conditions, the mutual exclusion or the resource holding or the no preemption or the circular wait. We've already talked about each one of them. Avoidance, implement Dijkstra's banker's algorithm, which this guy looked at the banks and he thought the banks worked very efficiently and they worked perfectly for a long time. So analyzing the banks, he found that every bank has customers. The customers come for loans. So as long as the bank can give a loan to somebody, no more than what the bank balance is. If the bank has 10 million, don't give a loan to one individual of more than 10 million. But the total, if you give it to many customers, you can go way past the 10 million. But the basic idea is that before giving a loan or before approving a loan, remember the way it works. Customers come in, they ask for maximum loans. They are approved, but they're not given the full loan. in one go. Then let's say, imagine that if somebody is going to build a factory, it is going to cost 5,000, for example. So they come up and ask for 2,000 to build the building. And then they might come back and ask for another 2,000 to buy the equipment and machines, and maybe 1,000. And once they have the full loan, then they start paying back. That's the only time they pay back. So now, once we approve the full value, none of these guys is given more than what the total bank has 10, but none of these guys here has exceeded the 10,000. Has never been approved for more than 10,000. And once they start working, then each one of them can come up and ask for a certain amount within the loan that they've asked for. So at the moment, this guy has asked for 2,000, so there's still 3,000 to go. This guy has asked for 4,000, so there's 4,000 more to go. This guy has been approved for 4,000, has taken nothing yet, so he could come tomorrow and ask for 4,000. At the moment, total given out is 6,000, those two figures, and obviously the bank had originally 10,000, so it still has 4,000 balance left. So if tomorrow this guy comes up and says, give me the 4,000 left, we can actually accommodate them. Or if this guy comes up and asks for 3,000, we can accommodate them. And once they get the full amount that they have, then it's just a matter of time before they start paying back. And we assume they'll pay us back immediately. So if you can accommodate all the remaining credit with what you have, we have 4,000 left. If this guy comes up, we can accommodate them, then they'll pay us back 8,000. Out of the 8,000, we can accommodate this guy, and he'll pay us back 5,000. Then we use that 5,000 to pay back this one. So if we can clear everybody, then we are in a safe state. That's the banker's algorithm. Every time a request comes in, say, what if we allocate or satisfy that request? Will it leave our bank in a safe state or not? And how do you know if our bank is going to be in a safe state? If the resources we have left in the bank will accommodate and satisfy all the remaining requests. Start always by the smallest request. Okay, we've done through that. We had a couple of examples of going through it, so we should go through it and find out whether to accept a loan or not, or request for a loan. And if it is, well, then we'll grant it, and if not, we don't. And it seems to work. This system, banker's algorithm, works on our resources. Our resources just you can assume that these are devices that we have in the system. Like we have 4 printers, maybe 5 disk drives, 8, whatever, other devices. And we have our programs that come up and request. This might say, I need 2 printers, and this process says, I need 3 disk drives. And they may be in kind of more complex systems where we say, right, that's what we have of printers, but we have also hard disks, and we also have plotters. And then a process can ask for those printer and maybe 1 plotter as well. But this gives the idea at its simplest form. But just remember that there may be more resources than what's being shown here. So, how good is banker's algorithm? Fortunately, even though if it works, it avoids deadlocks to a certain extent, but the jobs must state, we ask each program to tell us exactly what resources they need at the very start. They declare how much they need. Sometimes not all programs know. And sometimes that's not efficient, because a program might need these 2 devices or those 2 devices based on some if statement within the program. So we don't know. It's going to use only these 2 resources or these 2 resources, but not the 4 of them. But at the start of the execution, we don't know which 2. So we might have to give the program the 4 resources, just in case. And that's not an efficient way of doing it. So the number of total resources for each class must remain constant. The number of jobs must remain fixed. That's another problem. This is not a very dynamic algorithm. If the program's number of processes change, then we have to recalculate. If another new process is submitted for execution, We have all this calculation has to be redone again. Resources aren't well utilized because of the algorithm assumes the worst case, so keeps going, okay, what if you need this and what if you need this? Well, here, we'll give you the two of them just in case. Scheduling suffers as a result of poor utilization, so you'll end up actually, doing not great performance. Now, how do we actually detect a deadlock? In order to start dealing with it, we need to know first, do we have a deadlock in our system or just our program's running slow? So with the deadlock, we use it by the directed graph. So we'll draw a diagram, and we've already talked about drawing the diagram. So we'll have an example, like looking at one of the systems. Imagine if we have this kind of entanglement of directed graph of resources and processes, assuming these are the processes here and these are the resources. So this process needs that resource, but that resource is allocated to this process. This process already has this resource and that resource. So this process needs 3 resources. It has already 2 of them allocated to it, but it needs 1. That one is not available. Looking at this process, it needs 3 resources. It has 2 of them, but it doesn't have that one. That one is allocated to this process. So just out of this one, if we follow this arrow, this process needs that resource that's allocated to this process, that needs that resource that's allocated to this process. That brings us to the same point. That's a deadlock already there. But if we can't get rid of them, well, okay, but it's unlikely. Looking at this process here, it only needs 1 resource. If it can have it, it's out of the picture. But this resource is allocated to this process, and this process is not going to release it because it's waiting on another resource. So this one is also going to wait. So actually, it doesn't look like we're going to get rid of anything here, and we've already identified a deadlock, a circular wait. Another example. Quick example here, if you follow it with me. Usually, to remove these links, always go for the process with the least amount of resources, and that has all the resources it needs, and then we can remove it. So looking at this one here, process 1 only needs 1 resource. If it was available, but unfortunately it's not available, it's allocated to another process. So let's look at this process. This process needs 2 resources. It needs this one and that one. This one is already allocated. This one is free. So we can allocate it immediately, and we say now this process has those 2 resources, and once it has all the resources it needs, then it finishes, and we can wipe this and wipe this. It releases those 2 resources. We can also get rid of this process if we want. So that's one process gone with those 2 lines. So now, can we run this process? No. Well, yeah, this resource is free. If we give it to this process, it will finish and it will release it. So that's gone as well. That process is gone, that process is gone, and those 2, 3 links. So now that's free. We can now, it's only needed by this process, so we can allocate it to the process 3. So process 3 needs 3 resources. This one now we have this one, all we need is this. But this one is allocated to another process. And it's not going to release it because it needs another resource if it gets it. But it can't get it because it's already allocated to another process. And this process here needs this resource that's already allocated to this one. Back, I am at the same point. So there's a circular wait going this way. Once you find circular wait, then there's a deadlock. Okay, so it's easier actually to redraw and wipe, and you can then see what's left. There's a clear circular wait. What about this? You have a look. Tell me. Somebody think about it. Look at it for 30 seconds and tell me whether there is a deadlock or not. Can you follow the rules? Look for a process that has very little resources and has all the resources it needs, and clear it off. And the resource it has, release it and give it to another process and go from there. So is there a deadlock? No deadlock? What do you think? No, what? No deadlock? Okay. What do you think? No deadlock? Right. Show me, how did you reach that conclusion, that there's no deadlock? Where did you start?
Process 3.
Process 3.
Resource 3.
It has this resource.
Doesn't need anything else, so it finishes.
So it finishes, we can clear this, and that's available.
And then resource 3 will be allocated to process 2.
So resource 3 is allocated to process 2. So now, process 2, it has all the resources, so it will clear them, it will finish. That's going to be available now. We allocate it to process 1. Process 1 now has all the resources and everything goes. Yeah. So there's no deadlock on this one. Okay? Right, so there's no problem. Right, what about this one? One of you guys? Any of you ready to tell me whether there is a deadlock or not? Or how did you reach it? Come on. You go ahead. Process 3. Where is process 3? 2. Sorry. Process 2 needs 1 resource. And it has it. So that's gone. Why? Now that instance can be given to process 1. Okay, great. Process 1 now it has everything it needs. It's gone. Fantastic. So process 3 now already has that. Now it will be allocated this one when it becomes available. Process 3 finishes. Now process 4 only has 1 resource and it finishes. So there is a deadlock, right? There's no deadlock. Okay, great. So, all right, so practice these. Well, I'll have in the tutorial a couple of these drawings that I want you to go through and tell me whether there is a deadlock or not. And if there is a deadlock, as in this case here, you need to tell me what are the processes and resources that are deadlocked. So in this case here, I don't know where the deadlock is. I think it starts from here, there, this way. Yeah, so you'll have to write P3, R3, P4, R4, P5, R5, and that's the deadlock. So I need to be able to follow that deadlock. So you need to tell me what's the sequence of movements from processes to resources which implements the deadlock. Right, so recovery. That's basically, we said there's no easy and simple way of recovering from a deadlock. It always involves termination of jobs. So you can either terminate everything, terminate all jobs, or terminate the jobs that are only involved in the deadlock, or just terminate one of the jobs which is involved in the deadlock. One at a time. Hopefully, you terminate only one and you're out of the deadlock. Sometimes you might have to terminate the second one. But which ones would you terminate? Based on a number of factors. So these are the factors that you also need to be able to come up with those. So priority is an important thing. Get rid of less important jobs, the jobs that are not important. Consider the amount of time used by CPU, or the amount of CPU time used by the process. If it's more, well then, don't get rid of it. There's a lot of work to be done again. So eliminate the jobs that have used less time, less CPU time. Number of other jobs that would be affected if this job was terminated. So sometimes you terminate a job, it only affects one other process. But if you terminate one, it might affect 4 other processes. So go for the other one. The one that has more resources, holding more resources, terminated. Jobs that modify data should not be selected as victims for termination. So any job that really updates records and files, do not get rid of them. Starvation, on the other hand, his job is prevented from execution as it's kept waiting for resources that possibly will not be available for a long, long time or never be available. One example of that is the dining philosophers problem or table suggested by Mr. Dexter. And here it is, with the chops here, and our monks, friends, sitting there and enjoying their meditation, but also feeling hungry every now and again. So maybe, and these are the conditions that each philosopher, whenever they want to eat, they must have 2 chopsticks to begin eating. One on the right and one on the left, but not in this order, of course. But unless maybe anybody has any suggestions of how this might, any suggestions to these 5 people that hopefully they'll never starve or they'll never fall into a deadlock? Any algorithm, any advice that you might give them? Sorry. Each one at a time. Yeah, okay, it might be. It's not a very efficient way. And then one at a time in what order? So if you say one at a time, you can start now, and everybody says, okay, it's me now, I'm going to eat, and they all end up. Okay, well, okay. You'll also have to, consider that sometimes they don't feel hungry. So I think feeling hungry is a bit of random, but maybe we can control it to a certain extent. Yeah, if you want to suggest that.
Some kind of token pass.
Token? We pass a token between them, or maybe 2 tokens. One token is, guys, if we say you can eat and the other 4 cannot eat, that's not a very efficient way of using all these resources that we have. Yeah, a token is a good way, but then how do you pass the token? Well, to whom would you pass the token?
Always define a direction, always to the right, maybe.
Okay.
I don't know.
Yeah, so then you can say without the token, guys, you eat and then you're next, your turn next, so no one else can eat except him, and then maybe that's okay. Even without token, you can say eat in one direction, one at a time. Maybe, yeah. It's not an efficient way of doing it, though. Sometimes we want to see maybe 2 or 3 people eating, if possible. Anybody with any other suggestions? Okay, having some kind of a flag or a sign that says, right, I've used this one. The one on the right used it, so now can't use it again until this one uses it. Okay, well then we need 5 flags. Maybe just changing the position of the chopstick. Maybe, okay. Anybody else?
Instead of using chopsticks, the person can use spoon.
No, yeah. In my older slide, I had forks here, and then the problem didn't work, because you don't need 2 chopsticks. It's just the idea that you need 2 tools, 2 pieces of tools or resources that are shareable. Of course, if you use a dedicated one, why don't we have just 1 extra chopstick for each one of them, and everybody has their own? But this is the problem given, and these are the conditions, and you have to kind of think of, try and come up with an algorithm or a number of rules, or set some system for them to follow that doesn't require a lot of resources. That you might hear you've suggested using a flag. Okay, we might accept flag, but don't suggest to me 5 other chopsticks. That would be, duplicating the number of resources, which may not be possible in a system. Or maybe having somebody, maybe a waiter that goes around, or maybe even cutting down 1 person, just reducing the table to 4, maybe, it may not be also.
Picture like one of those Japanese places where the rice goes in front.
The table rotates. That's another possibility, but it's not available here, up the mountains, up in that area there. So you can suggest maybe every odd or even numbers that they eat, maybe if you go, or maybe skip every second one. So this guy can eat, the neighbor cannot eat at the same time, but that one can eat. That one cannot eat, but then this one, when this one. So, or maybe also suggesting, maybe considering the hold and wait situation. Remember the condition for deadlocks? If the guy, you might decide, okay, everybody pick the left, or maybe the odd number, say number 1, 3, and 5, pick up your left chopstick first. 2, 4, and 6, you pick up the right chopstick, or something like that. Or if you pick this one, and then you reach for that one, and if it's not available, if it's there, take it and you can do the eating. But if it's not there, then your neighbor is using it. Don't sit there waiting on them, holding the other one. That's hold and wait condition. Release this one, and wait until the other one becomes available. Maybe.
Can it be like this? Let's leave the first person out there. Let the other 2 persons meet and make a quantum for them. That in that amount of time they eat the food, and the another 2 person would be checking.
Possibly, yeah, you can have a quantum implemented, a stopwatch, hit it there, you have 5 seconds to eat, or 50 seconds, or it's possible, yeah. Okay, I'll leave this up to you. Think of, give me a couple of good solutions for it. I think I have it in the tutorial. Google the solution, see what other solution. Give me a solution that requires less resources. Don't come up with, fancy resources and stopwatches and calculators. Now, these guys out there, we just something simple. We want something simple, but that's guaranteed to work, that will prevent deadlock and will prevent starvation. Okay? And that's the last thing we have. So any questions, guys?
I just got me thinking about it.
All right.
I was thinking of maybe a kind of a sliding window protocol, but from what I can see, it's just at the same time, just only 2 people could eat, right?
Yeah, you can.
So I could use maybe a 3 slots window, but the one in the middle would be a empty space, so it would be always
you can.
jumping.
If this guy eats, that one can eat, and then whatever.
It moves, but the one in the middle wouldn't, the second slot would be a gap, is that something like that?
But always, also, guys, don't forget that they randomly feel they're hungry, so you can't say eat now, because they may not be hungry, and but just take that into consideration if you can. But if you can't, okay, we say, sorry guys, we can't accommodate you whenever you're hungry. You have to eat. Just so, as long as you don't starve. But if you can leave it up to them to say, now I want to eat. All right, can I eat now? And if they can't, when is the nearest time that they can eat, or something to that effect. But all right, consider all the options. Come up with the minimum, with the solution that requires the minimum resources to be added, or the minimum complexity. Well, as long as they can implement that complexity, that's okay. Right, okay, then before you go, let me just ask you a couple of questions now. Okay, give me one condition that is required in order for a deadlock to occur in a system.
Out of the 4 conditions?
Out of the 4 conditions, just name one, because he's going to tell us how to...
Hold and wait.
Do you want me to wait, or that's the condition? Hold and wait, right, okay. Wait and hold, right?
Wait and hold.
No, hold and wait, go on. Now, tell me, how do you actually remove this condition from the system? If we say we want a system that does not contain this condition, so we'll not have a deadlock. Okay, think about it, or I come back to you.
If you add an order to resources, so if you want 1 and 2, then you have to have 1 before you have 2.
That would probably prevent circular wait more than the hold and wait. How would you make sure that we don't have a hold and wait?
Don't allow processes to hold resources while they're waiting.
Yeah. How would we do that without damaging the system? You can't just say, hey guys, anytime you need a resource, if it's not available, release the one you have. That doesn't work as simply as that. I want to make sure we never get to that point. Anybody knows how to actually make sure our system does not have this condition of going and waiting for a resource while holding another resource? Any idea how do we get rid of that? No, we don't want to terminate processes that are halfway through execution without termination. Right. We'll come back to it. How do we remove the circular weight? Any idea? Without you. Any idea? How do we remove the circular weight condition?
Circular weight, you would need to choose at least one job to be terminated.
No. Guys, we're not talking about termination. We're going to talk about a system that never has a deadlock. So, we have 4 conditions. If we can remove one of those 4 conditions from our system forever, then we will never have a deadlock. One of those conditions is called circular weight. How can we run a system that we know for certain it never has a circular weight? Say again? Oh, we can. He actually told me a couple of minutes ago. Say it, tell us again. Yeah, so get all your resources in one order, in some order, in a list. And any process that needs more than one resource, 2 or 3 or 4 of them, go for them. Don't go for randomly, I'll take that one and then this one. No, go in this order. If you have 4 of them, go for the highest one, then the next one, then next. If every process does that, then we will never have a deadlock. Remember with that chef or those 2 users that need 2 resources. Why did we get a deadlock? Remember this process or this person who wants to cook or... that's the resource here. Resource 1, resource 2. Now, the first user, first process went for that one. It grabbed that one, took that one. The second process took this resource. That's why we got a deadlock. Because this one went for that, this one went for that. Now this one needs this. It can't have it. It goes in a wait. This process needs this resource, can't have it because it's already there. So it ends up into waiting. If these 2 processes, process 1 and process 2, we know they both need this resource and that resource. But what's happened? This one went for that, this one went for this. No, if they had both went for resource number 1 first, only one of them will get it. Whoever gets resource 1 now can go and get resource number 2. Knowing the other one cannot go for resource number 2 without having resource 1. So if you put this order, you say, guys, if you want these resources, go for resource 1 first. Then in this order, here, our resources are all listed. If you need any 2 of these resources, if you need 2 and 4, don't go for 4. You must go for 2 first, and then go for 4. So if these 2 guys, they both need resource 2 and resource 4, they can't go for 4. They must both go for resource 2. Whoever gets resource 2 now can go to resource 4. If you don't have resource 2, you have to wait. And therefore, we'll never have a circular wait. Okay, so each one of those conditions, those 4 conditions, there's a method or a technique or a way that will make sure we eliminate it. We never have it in our system. Remember, what about the unshareable devices? The devices that are mutually exclusive. How do we remove the mutual exclusive device from our system? We don't want to have in our system any device that's a dedicated device that cannot be shared. How? Say again? So we turn them into a virtual device. Is that what you said? Yeah. So we turn our devices into virtual devices. If we can do it, then that's it. We'll never have a deadlock. So you have to remember those 4 conditions. You must remember those 4 conditions. You must remember how to explain each one of those four conditions. And also, how do we actually eliminate any of those conditions from our system in order to ensure that we don't have a deadlock. Right. Okay. What else did we talk about? How do we actually avoid a deadlock? Deadlock avoidance. How do we avoid a deadlock? Oh, thank you. Thank you. Shukriya. Yeah. Or prevent.
Guarantee one of the 4 conditions doesn't.
That's preventing a deadlock. That making sure one of the 4 conditions is not in our system will guarantee we'll never have a deadlock. But that's not always possible. So instead of preventing deadlock altogether, we avoid it as much as we can. So how do we avoid a deadlock? using the banker's algorithm. Using the banker's algorithm. Each time there's a request for a resource, check if we do grant this resource or this request, is our system going to turn into an unsafe state? And if it does, then we would not do. We would not grant it. So that's banker's algorithm. And how do we detect a deadlock in a system? What technique could we use that help us detecting deadlocks in systems? Yeah, the directed graphs. Yeah, so using the directed graphs, and then you need to be able to explain how does it actually work. You need to be able, or maybe if you got a graph, you need to be able to, find out whether there is a deadlock or there is no deadlock in the system. And if there is, you need to be able to point out what's the sequence of processes that contain the deadlock. And how do we recover from a deadlock? Any idea? Recovery from a deadlock. At least, yeah, terminating one of the processes. The process that's really running happily and executing nicely. Is that the one you terminate? Yeah. Which one do you want to terminate?
If you know which one is causing problems, you can terminate that one, or you can terminate the one that's just wants resources.
Yeah. Okay. Thank you. Yeah?
That one who causes less damage to the system.
Okay. So it's just selecting which process do you want to terminate out of which processes, not of the entire processes, only, the ones that are involved in the deadlock, that deadlocked processes. That's the reason I asked you, did you mean the ones that are already executing and running? No, only the ones that are deadlocked. So the minimum amount is to check the ones that are deadlocked and pick one of them.
And aren't a database. Isn't a database.
Yeah, exactly. Well, thank you very much. Yeah. Now, which process would you select out of those deadlocked ones? We have 5 deadlocks. Which one? Give me one recommendation other than the one that's not writing to a database. One that has a lot of resources. By terminating it, it will release a lot of resources that might, release other processes. Any other suggestions? The one that has not taken a lot of CPU time. So get rid of that one. The least amount of CPU time has been wasted. Yeah?
One that is mostly just reading, just the kind of research that it is just about reading files or something like that, comparing to ones that
the one that's not writing to a database. One that's reading, that's fine, but avoid the ones that are writing. Thank you, Max.
One that has the low priority.
Yeah, go for the low priority ones. Yeah. Any more questions, guys? Okay. Thank you very much, and I'll give you the tutorial. That's something to read while you're watching your TV.